All right, well, today I'm going to offer you a video lecture because of weather and whatnot. So hopefully you'll enjoy this and get something a lot out of it. And it will help you um, with your homework and help you introduce yourself to limits. Now, before we get started, I just wanted to instruct on a quick review where we left off in our last lesson. Is that we wanted to figure out about trig, and I just had some quick review problems I just want to go through. We talked about trig last time. We talked about the unit circle, which you do have to know, but some of those things that we didn't cover, and I want to just see to make sure that you know how to do. So what we're going to do is we want to make sure that we know how to find what quadrant, if I give you the sine of theta, which is greater than 0, and the cosine of theta, which is less than 0, what quadrant would that be in? So this is what I normally would do, is I would probably draw out an axis, okay? And what I'm thinking about is, first off, sine, if you remember, is sine, all right, of theta is actually going to equal y. So it's basically saying where our y values, sine y, has to be greater than 0, okay? Well, y is greater than 0 wherever it's positive, and that's going to be in the first and the second quadrant, all right? And we're trying to figure out, okay, that's my M symbol. All right, where cosine, all right, which of theta, which we know equals x, all right, in our unit circle, is going to be less than 0. Well, cosine, I'll get a different color here. All right, cosine is negative. Cosine x, well, x is negative here, so in the second quadrant, and also the, all right, third quadrant. That's where x is negative. That's where cosine will be negative, all right, because that's what cosine is. Cosine equals x. So now the question is, what quadrant has both these characteristics? Well, that's what they're asking for. Well, what you do is you just look for and say to yourself, where do both of these, all right, coincide? And it just happens to be both in the second quadrant, all right? And so we'd say this would be in the second quadrant. And that's how you solve problems like that. Simply just draw out a coordinate grid and think about, all right, where is sine, where is cosine, or tangent, or wherever that may be, where those are located, okay? Another one I want to just talk about is how to find two solutions of an equation, all right, without your calculator, given cosine of theta equals negative square root of 2 over 2. Now, with this right here, we're going to go from 0 to 2 pi, so basically 360 degrees. Now, cosine we have is whenever you want to solve for an angle, and you want to solve for cosine, you need to use the inverse operation. Now, if you read through, which I asked you to do, but if you read through 1.6 and 1.7, or 1.5, sorry, 1.5, 1.6, what you notice is that they talk about inverses. And one of the properties of inverses is that when we have a function composed of its inverse, okay, composed of its inverse, that's what means inverse right there, that's going to equal the input. That's going to be the value inside. And that's how we cancel out different things, okay? That's why when you have a function, like for example, x squared, okay, for all x values, let's just say greater than, all right, are equal to 0. And then you have another function, which we'll say is the inverse, we'll call it g of x, but that's the inverse. That would be like the square root of x. And the reason why this works out, why they're inverses of each other, is that when you compose, all right, this square root of x inside of x squared, it's going to be equal x right there. It cancels each other out, okay? And so what we have right here is going to be, the square root of x, and we'll be squaring, okay, which will equal x. That's what we have when we compose those two values together, all right? F composed of g. All right, well now, let's say I want to solve for cosine. Well, cosine, all right, we want to figure out what the angle is. So normally what we would do is we would take the inverse cosine of both sides. So we would take the inverse cosine of cosine of x, or sorry, cosine of theta, and that would be the inverse cosine, all right, of this right here, the square root of 2, or negative square root of 2 over 2. And we have that right there. Now, the thing is that when you do this, you only get one possible angle, all right, when you have that. So what these do is this cancels out. You're left with the value inside. So in this case, the value is theta. So you have inverse cosine, and you have negative square root of 2 over 2. All right, and that's how you would solve it if you do it with your calculator. And the thing is that when you have this cosine, the domain of the inverse cosine is only from 0 to 180 degrees, 0 to 180 degrees. So we're looking for two of them because if you recall, as I said right here, one is cosine x. We're trying to figure out when this ratio, all right, square root of 2 over 2, is negative. And so essentially, we're looking for two different angles. One that we'll get right here, because the domain, all right, the range of or so the domain of the inverse, or the range of the inverse is from here to here, all right, and that's where we get our values. And so what we have from, all right, so what do we have here? Well, we're looking for values. Cosine is negative. Remember, cosine negative here in the second quadrant and also in the third quadrant. And so essentially, we're looking for an angle in this quadrant right here, so one right there, and one right here, all the way around, all right? And we'll call that alpha, all right? Going all the way around, that's going to be in the third quadrant as well. The thing is that both of these angles will have, all right, cosine the square root of 2 over 2. Now, if you recall, you can't use a calculator, so it's probably going to either be a 30, 60, 90 triangle, 90, or a 45, 45, 90 degrees. All right, 45, 45, 90 degrees, which is 1 to the 1 to the radical 2. Come on now. And this is 1 radical 3 and 2. Ooh. All right, well, which one will give you square root of 2 when you do ka? Well, that would be square root of 2 over 2 right here. It's a 45-degree angle right here, okay, which is pi over 4. Okay, so what we know is that this is a 45-degree angle. So what angle is from here? That's 45. Well, it's going to be 135 degrees. All right, so theta right there for the first one is 135 degrees, but we have to write this in radians, which is going to equal, all right, so, sorry, yep, 3 pi over 4. That's 3 pi over 4. And the other one going all the way around is going to be 225. So little alpha, that second one, is going to be 225. All right, because we're just going to add 45 to 180, which is 225, which is going to equal 5 pi over 4, and those would be our two solutions from there. One of them you would get when you take the inverse cosine. The other one you just have to understand that, yes, I have two different values going from 0 to 2 pi, because cosine is negative, this ratio is negative for two different angles, one in the second quadrant and one in the third quadrant. All right, so that was our quick little review of some trig. And so today what we're going to do is going to get to the nitty-gritty from Music City. We're going to talk about, all right, limits, okay? And these are objectives for this lesson right here. We're going to talk about the definition of a limit. We're going to hope to understand the difference between the value of a function at c and the limit of a function at as x approaches c. We're going to hopefully be able to find out how to evaluate limits graphically and numerically, and hopefully also, all right, not hope, we will determine when a limit does not exist. So without further ado, here we go. What is a limit? What is a limit? Well, a limit, all right, if you never heard this term before, limit is what I would say the intended height of a function. Now, the key word is intended height of a function. So when you're finding a limit of a function, you are finding what is the y value, because that's the height, okay? So where is this function going? What is the value of y, all right, of the function? What is the intended y of the function? Now, intended is, what does intended mean? It means where does it intend to go to, all right? Where does it appear it's going to? All those different things. Well, that is what separates a limit from a function. In that when you have a function, you're talking about the exact value of a function. And that's why a limit you have in books is they say the informal definition is more defined as this. If f of x gets arbitrarily close, all right, close, to a unique number L, okay, so f of x, which is our y, all right, becomes arbitrarily close to a unique number L as x approaches c, okay, so our x value, all right, the x value has to approach c from either side. And what we say the limit of f of x as x approaches c is L, that y value, remember that as the y value. That's our intended height. All right, that's our intended height. Okay, and then we write this in this limit notation. So this is what it would kind of be. All right, so if we had a graph, all right, let's just look at this graphically. All right, and my axes are not exactly perfect, so I apologize. All right, but let's say I had a function. We'll just give us a little tiny function. We'll say f of x, we'll say is x squared. All right, x squared, that's a parabola. And so if we plot some points here, all right, like that, we can draw a parabola like so. All right, that. And this is what this is saying. We know, let's say we're going to find the limit. Okay, we're going to take the limit as x approaches, let's give a value of 1. Okay, we'll do a 1 of f of x. Now, what we know is that we know that f of 1 is 1. But a limit is not looking for what the value is. Okay, and that's what a function is. All right, a function, if I plugged in f of 1, yes, into that function, it would be 1 squared would equal 1. Now, that is a function. All right, that gives us the value. However, a limit is not looking for the value. It's looking for where is it going? How is it getting arbitrarily close? What value is it approaching? Now, that might be 1, but not all the time. We're going to talk about that a little bit more. So, for example, if I were to do this limit, what we actually have to do is we are trying to figure out what happens, what is our y value, all right, approaching as I approach a c value. Now, the c value in this case is 1 from either side. And so what we would do is we are actually going to be taking values of c, okay, of 1, and we're going to be approaching from either side. Well, either side means we're going to approach it from the right side of c, and we would have a left side of c. And we have to approach that value from both sides, So what happens as you are approaching, as you start plugging in values of c from the right. So a value that you would plug in, so as the limit, let me write this as it's all right, the limit as x approaches, in this case 1, because that's our c value, c equal 1 here, c equal 1 there. And we put to the right side, we put a little plus sign there of this function fx, which is a parabola. We are essentially trying to figure out what is happening as I plug values, all right, as I start getting values closer and closer to 1 to the right. So we're plugging in values like 1.1, 1.01, and so on and so forth. So if I were to do a table of values, I would be plugging values that are getting closer and closer to 1. So I maybe start at 1.1. That would be to the right. Then I would find out what was the value at 1.01. And then I would put another value at 1.001. And as they get closer and closer, we see that this value may be approaching like 0.999. All right? And 0.999 appears, as you see this, as we look at our y value, it appears that it's approaching this L value, at least to the right, which appears to be 1. So what we would see the limit as x approaches 1 to the right is 1. We would do the same thing, all right, and we would approach the same, do the same instance, but we would go to the left side as well, because for a limit to exist, we have to get arbitrary close to a unique number L as x approaches c from either side. So that means as I approach this value, 1 from the left, and we put a little minus sign there for left of f of x, all right, we would do the same thing. So if I would draw a little grid, I should put a y there for so you understand what we're getting there, all right? And what would happen is we would see this, we would see that our limit, that's approximately approaches 1, and as we go here, as we plug a value, all right, of x right there, and we start plugging values to the left of 1, So value like a 0.9, all right? It's because we're going this way now, approaching 1 that way. 0.9, 0.99, that's pretty close to 1. And we can get even closer, like 0.999. And as we do that, you might start realizing that, okay, as we do this one, all right, actually this would probably be approaching not 0.99, that's actually probably going to be like 1.000, I apologize. All right, if you look at this graph, yeah, what is it going to look like? I'm totally screwed up. All right, that's probably like 1.001. This one, on the other hand, as you start plugging in values, I'm sorry, you should have stopped me. You couldn't. All right, as you start getting in values close to here, you realize that this value from the bottom is probably approaching values, yeah, of point. Now this one of our y values are getting closer to 0.999, which would be approximately also equal to 1. And so both we notice that from the right and left side is approaching a unique number L, and so we would say this limit would equal 1. Yeah, and that's what a limit is. A limit is a value you get infinitely close to, all right, from both sides. You're trying to figure out what is the y value, what is y approaching, what is it getting close to as you get closer to the c value here. Now that's important. Now that's important because it allows us to find undefined values. Now this one was continuous and was pretty easy, but let's take a look at some other ones that maybe be a little bit more difficult. Okay, so that's what we have here. So what we have is, all right, we're going to, all right, take this limit. We're going to kind of look at this algebraically, and we're going to put this on Desmos. So if you have Desmos, you want to take it out, you can pause this and then take that out so you can start using it, maybe follow along at home. So what we're going to do is we're going to try to figure out, all right, where is this approaching? So essentially, what we need to do is we're going to take this out, and I have Desmos ready to go. All right, so if you have Desmos out, all right, there we go. All right, and what we're going to do is we're going to take this, and we're going to plug in some values. So I want to figure out what is the limit of this function right here. Now, if you've ever used Desmos before, I have some other functions right there, but you're just going to go here, type in Desmos, you can use it as a user, whatnot, put in anything you want, and we're going to do a function expression. So I add a little plus button. And we're going to do is y equals, I'm going to punch this in here. I'm going to put parentheses for the x, or the numerator, x minus 4. Okay, go like that. We're going to divide by, all right, the square root. Now, square root in Desmos, I'm going to go x to the 1/2 power. So you have to use a little caret symbol and go 1 divided by 2. All right, put it over. All right, more. All right, minus 2, and we have this graph right here. Now, we want to figure out what is happening as we approach 4. All right, 4. Now, if you see this value right here, okay, we are investigating what is happening as we approach 4. And to do this, if you press that little button I have, so if I go right here, you press this little edit list button, you can press in a table, you can start playing a table of values here. What I can also do is I can start moving a little point closer and closer to 4 and see what happens. So essentially, when we find this limit, as x approaches 4, I'm trying to figure out from the right side, where is this coming from? What values do I see as I get closer and closer to 4? All right, as I get closer to 4, 4.1, 4.08, and you can see that it appears to be going to, look at the y value, 4, right? Well, if I actually plug in 4, it's undefined. It's undefined because you can't divide by 0, right? So if you actually plug in 4, it's undefined because you can't divide by 0. But it appears that even when I go to the left side, as I get closer and closer to 4, it appears that also, you get 3.992, it's also going to, here's getting closer and closer to 4. So to verify this, we're going to plug in values, what they ask us to do. Okay, I'm going to plug in here, and then what you can do is just go right there. And we're going to plug in 3.9. So I'm going to plug in 3.9. And you see that that is the value. If I plug in another value, 3.99, you can fill this table in your notes if you want. And you plug in 3.999, you notice that, yeah, this value really does appear to be going to, all right, 0. Or sorry, not 0, 4. However, if you get even closer, if you go like 3.9999, now it doesn't say on the table, if you looked at our little value that we didn't have to do that, but right here, it just keeps on getting closer and closer and closer to 4. But yet, 4, unlike the previous problem, is undefined. So the value at 4 is undefined, but yet it appears, at least when we approach from the left side, all right, because that would be the left side of 4, all right, left side of 4, as I get closer to the left side of 4, our value is approaching 4, right? Appears to be approaching 4. So I'm going to put that over here, all right? I'm going to say this value is 4, all all right? And that would be to the left because that has a minus sign. So we would write out that limit, all right, to the left is 4. Well, let's continue. All right, let's find out, because for a limit to exist, it has to approach the same value from either side. So that means I have to plug in 4.001, and why am I going backwards? All right, 4.001, all right, 4.00, oops, let's go like that, and then 4.1. And you can see even right here, as we get closer and closer to 4 here, yeah, it appears to be approaching 4 as well, both sides. So this side also is 4, because the limit as you approach from the left side, remember this is the left side, all right, this is the left side, all right, so left one side limit, and this right here, when you see that right there, this is the right side of 4 with a little plus sign. This is the right side of 4. Because we're approaching the same value from both the left and right, we know the unique number that f of x is approaching is 4. The limit is 4. Even though the value f of 4 is, well, look it in there, 4 minus 4 over the square root of 4 minus 2. It actually is 0 over 0, which is undefined. We'll talk about more what that is in a little bit. But yeah, there's an undefined value there, but yet the limit exists. Well, we can do that for a bunch of them. And this is where I say the ultimate definition. This is where you use limit notation. So this is essentially the definition of what a limit is. In order for a limit to exist, a value has to get arbitrarily close to a unique number from both the right side, all right, the right side and the left side of C. So you're approaching the same value, the y value, from the right side and left side. If both those are the same, then we know the limit right here is going to equal L. So if both these approach the same value, all right, the same value, which is L, then yes, the limit itself. This is what we call a two-sided limit, all right, two-sided limit, all right. When you just don't have to see any plus or minus there, two-sided limit will equal L itself. So if you want to go through, I have a bunch of other problems right here, a bunch of other examples. If you want to try these out, I'm just going to show you on Desmos how to do these and what they're going to be. So let's try natural log of x, all right? And we'll go to this one and this one. All right, so natural log of x, I have Desmos right here ready to go for us, all right? And when we have this one, so I'm going to take this one out. And so essentially we're looking for what is the value as we approach this natural log of x. So if you take this in, I have it ready to go. And so we're approaching 1. Now, when you approach 1, we're going to approach it from the both the right and left side. Okay, so here's 1, and so from the right side, so from the left side, we're talking about values like, right, close to like 0.99 and so on and so forth. So if you go like this, all right, 0.9, and then we're going to go 0.99 and 0.999, and what you see is that what is getting closer and closer to, it appears, well, that's kind of hard to see. We get that right there at 1, right there. As we get closer and closer to that, all right, we see that it's getting closer and closer. It appears to be, all right, oops, wrong value, all right, 0.9999, all right. Yeah, it's getting really, really small, and it appears to be going to 0, right, because there's a 0 there. The limit as our natural log of 1 is 0. And so if you actually plugged in, all right, 1 there, it is actually 0. And so that makes sense that it is approaching that, because it's continuous there. If we go 0.0001, all right, 0.001, all right, 1.01, and then 1.1, all right, you can see that, yes, also, as we get closer and closer to 1, it is going to 0. Okay? Well, yeah, we can see that in the graph as well. All right? All right, so that's that one. Well, I have another one. You have this right here. All right? We'll put that one right there. Oops, I'll close this off. So let's try this next one since I have it one that's showing right here. Okay? And right here, we have another one, which is going to be that one, all right, with the square root again. All right, now this one's a little bit more strange, okay, because we're going to be approaching at -6. So if I graph this one, I have to move my graph over a little bit. All right, we're going to look at -6. Now -6, this looks a little weird. Now this one, it appears to be approaching, all right, really leveled off right here. It looks almost a straight line, but it's not. negative 0.125. That's what it appears to be going to as I approach from the right side, and as I approach it from here to the left side. Yet as I get to negative 6, we know it's undefined because you can't divide by 0. So I plug in negative 6 here. All right. Oops, that's the wrong one because I should have a plus sign there. That actually would be defined there. Apologize. That should be a plus sign. Okay. All right. So when we have that one also is going to be there. So if we plugged in a value, all right, to that to the right of negative 6, or to the left, to the left first. So left would be negative, all right, 6 point, all right, 1, and then negative 6 point, all right, 0, 1, and then we get a little closer, all right. And sometimes I just hate doing this. Let's just get crazy. All right, let's just get close. And you can see, yeah, it approaches negative 0.125, negative 1.25. To the other side, so if we actually plug in negative 6, it doesn't work. But then if we go to the other side, which would be like negative 0.5, 5 point, I'm just going to get really close. And you can see that and confirm it. Yeah, it approaches the same value from both sides. So it doesn't matter. As you do that, yeah, our limit in this one appears to be, all right, appears to be negative 0.125, negative 1.25. And this limit right here, this limit was going to equal, all right, 0. And we can do this for all the other ones, all right. Let's try that one right there. Plug in a 4, that. You can see that I have for this one. We're going to check it out at 4. So if I move this over here, we have 4, and I already have that filled out. So as we approach 4, you can see that, what does it look like? It's approaching, what do you think? 0.2, yeah, it appears to be approaching 0.2. All right, 0.2, even though 4 is undefined. All right, so the value there, F4, is undefined, but yet we can say that this limit, yeah, when we fill out the table, yeah, this limit is approaching 0.2. All right, 0.2. And if you do the e, doesn't matter what type of function you have, right? E to the x minus 1 over x. X approaches 0. You can try this out yourself. All right. Again, this one. All right. Once again, what we're going to be approaching, we are approaching 0 in this case. So getting closer to 0. All right. So I'm just going to plug in 0. Yeah, obviously it's undefined. All right. E to the 0 power is 1. All right. Let me graph this right here. So as we approach 0 right here, well, it looks like there's a value, and it appears to be getting closer and closer to 1. If you kind of look at that, it appears to be getting closer and closer to 1, but yet the value is undefined. And just to make sure, we can plug into the left be 0.00001. All right, I'm plugging 0 just to verify it's undefined, and then we'll go 0.00001, and we can see, yeah. I'll just delete these other ones. All right. Yeah, this limit is approaching 1. This limit is 1. Making it closer and closer in doing that. So the limit is equal to 1. And so that is how you can solve limits numerically. All right? Because we are using what the definition of a limit is. All right? In doing so, we're finding a y value when it becomes, what is the y value? That's what a limit is. When it becomes arbitrary close to unique number L as x approaches c from either side. All right? And that is what we have there. And we are essentially using this definition. What's happening to the right? What's happening to the left side of C? Are these values approaching the same value? If they are, that's L. This is different than the actual value. It is not the actual value because the actual value may or may not exist depending on the function you have. Now we did that numerically, we saw that graphically, but you also have to be able to solve these values. So if you were asked to find and you were given a graph, all right, what is happening here? Well, if I ask you to find what's the limit of this function, let's say this is f of x, all right, as x approaches 0. So essentially what's happening, we're looking for what is the value of y, all right, so we're looking for the y, this y-axis, as x goes, all right, to 0. So as we approach to the right, what happens to our y values? Well, as these values start going in there, we can see that these values appear to be going to that value right there, which appears to be 0. When you approach it to the left side of 0, as we get closer and closer here, we see that our y values, yes, are also approaching. It appears to be that value right there, which is also 0. So we'd say that this limit of f of x as x approaches 0 is 0 because the right and the left side are approaching the same value. Another example, okay? What's the limit as x approaches 1? Well, 1, once again, we see that there is an undefined value, but then it's defined down here. So I'm going to skip down here. Find, if it exists, f of 1. Well, f of 1, if I actually plugged 1 into f, this is defined. That is the defined value, which equals -1. This is where sometimes calculus students get a little crazy, go, what? Yeah, that is -1. That's what's defined right there. But yet, the limit is not what the function is, it's what the intended height it is. Where does it look like it's going to? So as I approach 1, as my c values approach 1 to the right, so we have to look at that. What happens to the right? As x approaches 1 to the right, it appears that this limit, all right, is going to go to, what is that value? It appears to be approaching like 2, right? It appears to be going to 2. All right, so we see that limit is going to 2 to the right, and if it matches when x, all right, approaches 1 to the left, what is that value as x approaches 1 to the left? So if I go this way, get closer to 1 to the left side, I also see that this value, as I start plugging these values in here, this is also going to 2. Because these values are both going to the same value, this is our L value, all right, and this would be 2. So the limit is 2, but yet the value of the function is -1. Crazy, isn't it? All right. Well, this then leads us to, all right, help us define when limits do or when they may not exist. We know that they exist, all right, when they approach the same value from the right and left side. The thing is that, well, when do they not exist? Well, a limit doesn't exist for the very same reason when it does exist. A limit will not exist if it does not get arbitrarily close to a unique number L as x approaches c from either side. So if you notice that you do not get the same value from the right and left side, all right, you do not get the same value, it does not appear to be approaching the same value, then guess what? The limit as x approaches c of x does not exist. It does not exist. And when will that occur? Well, there's 3 instances. One is as x approaches c from both sides, you notice as, for example, if you approach like 0 here, you notice that you get a vertical asymptote. Okay, it increases or decreases without bound. So right here, since from the right side and left side, this right here, as we go here and here, we notice that our value does not approach a single value. All right, it does go to infinity, both sides. So I guess we could say it goes to infinity. However, is this a unique number L? No, this is not even a number. Infinity is not a number. Okay, it is a thought that of something very, very large. It's boundless and it's going in a positive direction. So we would say infinity. All right, it diverges, what we would say, but that is not a number. It is infinity, and therefore we'd say this limit does not exist. But it is approaching infinity from both sides. Okay, it is approaching infinity from both sides. Another instance where limit doesn't exist is yes, when it approaches 2 different values. Absolute value of x over x is a very, very common function. You'll see. Make sure you know this. So as you approach 0, okay, you notice that as x approaches, all right, 0 from the right side, you notice that my y values right here appear to be going to 1. So we would say the limit to the right, all right, would be 1. However, as we look at over here, as x approaches 0 to the left, as I go this side, all right, that way, we notice that my y values right there approach a different value. And actually, we would maybe call this m, because this m value is actually -1. We're approaching 2 different values from the right and left side. When you approach 2 different values from the right and left side, this limit does not exist. Though, all right, we'll talk about this more later, but though, all right, the right side limit does exist and the left side limit does exist, but the both 2-side limit does not exist. All right, because you need to approach the same value from both sides. The final instance is good old trig. Remember sine, if you draw a sine graph, all right, sine oscillates between, all right, 1 and -1, all right, 1 and -1. And so as you plug in values, and 1 over 0 is actually undefined as infinity. And what happens as you get closer and closer to 0 in this case, you notice that these values start they're oscillating between 1 and -1, 1 and -1 from both sides. They do not approach a single value. They do not approach a single value. This is what's called oscillating. All right, this happens a lot with sine and cosine function when you put infinity inside of them, or 1 over x, boundless value. So this one does not exist because it does not approach a single value. All right, so these are the 3 instances where a limit does not exist. Boundless, vertical asymptote, okay, increases or decreases without bound as you approach the c value. All right, it goes to 2 different values when you approach c. That would be a gap or a jump in a graph, or else it just oscillates, doesn't approach a single value. Okay, so those are the 3 instances. So with that, without further ado, our last thing we're going to do in this lesson is use this information. So for example, if I were to ask you, given this graph, find if it exists, the limit as x approaches 1. Okay, find that it approaches 1. Right here, we notice that here is 1. All right, this is 1. And so if you look at this right here, and as you approach 1, and I'll be very careful, as you approach 1 right here, you notice that what is the value getting closer and closer to? All right, it appears to be zoning in on this value right there, which appears to be -5. It appears to be -5. Yeah, -5. All right, -5 is that. What is f of 1? F of 1 appears also continuous there is -5. Now that's interesting, so that is true. Now if I switch this up and said, okay, what was -1? So if I change this up and write in a different value, okay, so I'm going to switch this up right here. I'm going to erase that right there. All right, and I actually think this is what I was supposed to have. All right, but I screwed up. What we have right here, let's say I went to -1. All right, let's say we approach -1. Well, -1, as I approach it from the, all right side, you see that this value, as you approach it from the right side, all right, so as x approaches -1 from the right, it appears that this limit, all right, okay, of the function, I'll write this out, of f of x, this is going to, well, go down here. It appears to be going to, what is that? It appears to be going to -7. It's going to -7, my friends. It is going to -7. And as we go to the limit, as x approaches -1 to the left, does it go to the same value? Well, let's check this out. So right here, as I go there, what happens is, as I get closer and closer, it's going to, oh, no, wait, look at this. It is going to, appears to be, my friends, it is going to -2. Uh-oh. Are these 2 values approaching the same value? Well, to the right, it's going to -7. To the left, it's going to -2. They are not equal. Therefore, this limit does not exist. This one does not exist. The reason why, it approaches 2 different values. Does f of 1 exist? Well, f of 1 does exist. This is an open circle. This is a closed circle. F of 1 is -7. All right, because it's filled in there. So it does have a value at -1, but the limit does not exist. All right, because it approaches 2 different values. All right. So here we go. Here's a little example. This is what we would like you to do. So evaluate this graphically if possible. If the limit does not exist, explain. So why don't you try this out? All right, you can pause this. Okay, this is a vertical asymptote, just so you know. This is going to infinity, so it's a vertical asymptote. All right, but find these values, okay, and see what you get. All right, so try that out. All right, pause it now, and then I'll start up in about 3 seconds after you restart it. All right, well, we're back. Hopefully you paused it. If you didn't, well, then you just missed out on your own learning. All right, so let's check these out. Well, what happens as x approaches -1 to the right? Well, -1 is right here. We're approaching from the right, so that means I'm looking at the value up there, going here. It appears to be going to 1. So if you put 1, you are correct. As you approach 0 to the left, so 0 is right there. Okay, it's approaching to the left, so it means I'm going here. And it appears that that value is also going to 0, so this one will be 0. As x approaches 0, now if we want to do this, the difference between this is a left-sided one, this is a 2-sided All right, that's the difference. So in order for this one to exist, it has to be approaching the same value from the right left side. Well, as we did that, yes, it seems to be zoning in, bringing it on in at 0. So there we go. There's 0. Okay. 2, all right, 2, we're going to approach 2 from the left. All right, so I'm going to go 2 to the left here. It appears to be going to 0 as well. All right, so it's right there, whatever that value is. That's the limit. It's going to be 0. Let's go negative 1 over here to the left. Negative 1 to the left. Well, negative 1 right here. As I plug in here, it is, well, it's getting down. It's going down. It's decreasing without bound. This one does not exist. All right, why? Because it's going to negative infinity, right? It's going to negative infinity. All right, it's decreasing without bound. All right, does not approach a unique number. All right, decreasing or diverging, if you want to put. It diverges there. Doesn't it go to a single value? So I'm going to just put diverging. All right, diverging. Okay, decreases without bound. Either one diverging. But that's why that one does not exist, right? Vertical asymptote. Number 2, we're at 2. Now at 2, all right, once again, this is a two-sided limit. We found that right here, the left side limit is 0. Let's find out at 2. Well, here, we're just going here. Now, there is no value here. There's no graph here. Whatever I plug in here, there's a question mark. What is the y value? What's the y value? I don't know. There's no value here. Uh-oh, this one does not exist. Why? Because, all right, does not approach the same value from both sides. All right, does not approach the same value from both sides. Not same value from both sides. Okay, both sides. All right, and then finally, let's just switch of colors because it's getting all over here. All right, let's approach 1. Now 1, what's happening? Well, right here, as I approach 1 to the right, remember there's a two-sided limit again, two-sided. So we have to go to both sides. So as I approach here, from the right side, my y value appears to be going to limit equals 0. But as I approach right here, where is that going to? It appears to be going to 1. All right, I'm going to put a different one because it's a different value. It goes to 1. So as x approaches 1 to the left, it goes to 1. As I approach x to the right, all right, right here, it's going to 0. This one does not exist. Why? Because the left and right side do not approach the same value. It's the same reason up there, and you can look at that one. And finally, what is f of 1? F of 1, f of 1, well, where is it? Right there, f of 1 is 0, all right, but the value exists. Remember, f of 1 is what is the value? What is the value? The value is 0, all right? But the limit is not the value, all right? It is where you appears to be approaching the intended height of the function. All right, well, I hope that made sense because we are done. All right, the things you should know is the definition of a limit. All right, we talked about that, all right? Get arbitrarily close to a unique number L as x approaches c from either side, okay? The difference between a value of a function at c and the limit of a function. A function at c, all right, if you didn't get it, is the actual value, all right? A limit is the intended height, okay? So a function, actual value, all right? And the limit is the intended value. Value is not the actual value, and I'm spelling this very, very poorly. Value. All right, sorry. All right. How to evaluate limits? Graphically, numerically, I think we did that. And determine when limits do not exist. We talked about that as well. All right. 2 instances is vertical asymptote, increase or decrease without bound. All right. A jump in a graph, approach to 2 different values, or else you have oscillation. Oscillating. And that's what we got there. All right. So it's such a question that you can answer on yourself. What is a limit? How is finding a limit different than finding the value of a function? We already kind of answered that there, but these are the questions you need to make sure that you understand, because that will help you, and will be the questions I keep on asking as we continue on our mathematical voyage in discovering limits. All right, then finally, your homework. There's something on page 75. This is in your syllabus or in your homework, actually, homework assignments. We are now following this. This is going to be done. It's supposed to be done at the end of the week. That's our week 2 homework. All right. There's 2 assignments. This is the first of one. The one that I asked you, this is right here. Those are the ones you really, really want to do. Very, very possible those will be on test. These will not be on test because you have to use your calculator to figure them out. Filling on table, but these you should know how to do given a graph, all right, and be able to solve those. So, all right, hopefully this made sense. Hopefully you enjoyed the little video. Hopefully it wasn't too boring. A lot of hoping here, and hopefully we'll have class again soon. All right, well, thanks again. Have a great night. Be safe, and we'll catch you on the flip side. All right, good luck and God bless.